There's no short answer to how to solve a projectile problem because projectile problems can be couched in a bunch of different ways. I'm going to run you through what I teach my undergraduate students in classical mechanics. The video itself should have a lot of useful information for you. You can stop at any time when you view it. But I'm going to run through things. I'm not going to go through them at the speed with which we would do in a tutorial session. In about an hour or so, I could run you through these things so you understand everything completely, have a good idea how to work problems, can work a few practice problems, and then we can talk about them. I'm going to share my screen now. And you should be able to see what my screen is. And I'm going to open up the things that I describe to my students. This is those basic points that I mentioned in the text in the answer. I'm going to go through here. The basic idea is how it flows from one-dimensional kinematics to 2 dimensions, and focus on the fact that there's a small set of equations that are useful, but choosing the right one is very important for being able to solve a problem quickly and accurately on a test or in any situation. But the good news is there are very simple methods to use to select the best way. With a little bit of practice, you can get these. So the first thing to be familiar with and comfortable with is what projectile motion is. This shows 2 balls, a blue ball and a red ball. The blue ball is being launched out to the side with some velocity, and the red ball is being released at the same time to fall down. And the thing you notice is that the ball that falls down and the ball that goes out to the side both fall downward at the same rate. The only difference is that the blue ball continues to travel outward in what's usually called the x direction at a constant speed. The way we analyze this is to break the motion into components and treat the x and the y dimensions as independent dimensions and have those linked by time so that we can get a picture of the full motion and solve any problem we want to solve. Classical presentation of a projectile problem is this. Something is launched from someplace and lands someplace else. It's launched at some angle with a launch velocity, and it goes along, and its velocities in the x and y direction evolve at the max height. The velocity in the y direction is 0. The constant gravitational acceleration is downward. These are the one-dimensional equations you should be familiar with before you start doing projectile problems. You should have done one-dimensional motion, a velocity equation, an x equation, and an equation that involves the squares of the velocities and the acceleration. You need to have these available if you're taking a test. If they're given to you, great. If they don't, the good news is you can derive these quite quickly from the definitions of the acceleration of velocity and a little teeny bit of calculus. Do a couple of integrals. You can get these. I can step you through how to do that. So if on a test you don't have these available, you can get the equations yourself. The third equation takes a little trouble to derive. You'll really need to just know this, even if they don't give it to you. It's helpful to remember this if you recognize this is just the equation for the conservation of energy. If you multiply this times the mass, it's just the conservation of energy equation. So for 2-dimensional motion, projectile motion, you have the 2 sets. You start off with the 2 sets of kinematics in the x and y direction. For projectile motion, they simplify. There's no acceleration in the x direction, and the acceleration in the y direction is constant at minus g. So these things simplify to the projectile equations, which has a very simple constant x velocity, and the x position is given by what you would get with that constant x velocity. The y equations are the full kinematic equations for that dimension, the simplification being that the acceleration is constant and is minus g. One other equation is extremely useful for solving problems, can make you get the answers, help you get the answers very, very quickly. It's called the range equation. The range equation says that the range, that is the x distance it travels, is equal to the simple formula, the square of the magnitude of your initial launch velocity times the sine of 2 times the launch angle divided by the acceleration of gravity. These equations, coupled with this equations, allow you to solve any problem that you want as quickly as you can. I'm going to show you, so you can look at it at some later time if you want, how to derive that range equation. There's just a couple of steps. I can walk you through that so you can understand that, but the main thing is to have it available. And it's helpful to understand where it comes from. Now, you don't have to just use equations. there are online a number of resources. Like this resource is at the University of Colorado. They have a number of simulations on the web that you can access and you can use. And I've got one that should come up here in a window. This should be showing up on your screen. This is what you get if you go to that link, and it's got an introduction and some other things. You click on the lab, and you can do problems like this, enable you to do problems like launching something. You click the button, and it launches a cannonball, in this case, at a certain velocity with a certain angle. And you can change the angle and launch it again and see where it goes. Not only can you see where it goes, you can use this thing to go down and see what those final conditions are. So you can check to see if solutions that you're doing are working, or you can just get the feel of how things go. Like you can find out that the maximum range comes up when you have 45 degrees launch angle. And I'll turn it back a little bit so you can do that. You can check the way you solve problems. Another kind of resource that's available, I have for my students developed some applications. This is a MATLAB application that allows you to calculate any projectile problem, and you just click the button after you put in some values, and there's some default values, and it plots what happens and then puts out in a table everything that goes on. You can launch things from some meters up. That was 20. You can launch it you can put in launch it from the ground, see what happens, and do that, and the table fills up with what the values are. You can input the velocity and the launch angle, like many problems give you. Let's do, say, 45 degrees. Click the button, and it does that problem and gives all the answers, the things you need to know, with initial velocities, final velocities, ranges, times, etc. So there are a lot of resources available on the computer to help you check your answers. Now, you don't want to be using things like this on the computer. You won't be able to on a test, but it's very helpful when you're working problems, getting used to things. Solving problems is easy if you have a method for doing it. First thing is to read the problem very carefully and figure out exactly what they're asking you. Draw a diagram so you see it in your mind. Choose an origin of the coordinate system. Usually this is x0 equals 0, y0 equals 0 at time 0. Sometimes it's different, but that mostly works. Then decide on the time interval they're asking about. What is the path that the problem is asking you about? Remember that the problem is simple. The acceleration is only downward, and it's g. Then you examine the x and y motions separately. A very helpful way to get to the right equations is to list down the known and unknown quantities, remembering that the x velocity never changes and the y velocity is 0 at the highest point. But then from that list, you can look to see which equations have the everything known except for the unknown that you need to find. And that's the equation that you want to use. That's the plan on how to proceed. This is an example problem that is given all the time. Somebody driving a motorcycle off a cliff at some velocity, a 50-meter high cliff, and the problem says, how fast? Now, I've underlined this because when you're reading a problem, you say, they're wanting me to find the velocity. And then it's going to have to go 90 meters from the cliff and hit the ground. The strategy for problems like this is always the same. You first find the time it takes for the thing to follow the distance, use that time in the position equation in the x direction, and get the distance. The other kind of classic problem that you'll see in projectile motion is what's called a projectile. You launch something with an initial velocity at a specific angle, and then you want to know things like how high does it get, how long does it take, how far does it travel, etc. This problem shows you the kinds of things that a problem like this can ask you. What's the max height? What's the time to travel? How far away is it when it hits the ground? What are the velocity vectors and acceleration vectors? These things you will always know because you know at max height the velocity in the y direction is 0 and the velocity in the x direction is what it started off with. And the acceleration you always know. So some of these things are very easy to answer if that's what they ask you. But if you need to work the problem, I worked them for you here. You can look at these yourself at your leisure. But this is an example. There are two different ways that you could solve the problem if somebody says, tell me the max height. One way is to go through the time, get the time that it takes to travel to the max height. That's the time that the velocity needs to get to reach 0. And that's given by this. And you find the time it takes to reach the max height. Then you use the y position equation to get what that height is actually going to be when it reaches the max height. Another way, a faster way, and a way where you might not make as much errors, is to use the equation that has the squares of the velocities in it. And that one just has the initial and final velocities of the points you're trying for, and the distance and the position, and everything in here you know. All right, except y max. So you rearrange that equation and you get an answer. It's nice to be able to do it two ways, because you could compare this answer with that answer. And if you get it both ways, you know you probably got the right answer. And you can look at this yourself, how to go through finding out what the travel times and all those kinds of things are. The other kind of problem that you get a lot, and I get a lot, is a problem where somebody's flying along at some fixed vertical height at some velocity, and I always give my students the velocities in miles per hour so they get a feel for what it is, and I convert it for them to meters per second. But you may need to do that conversion. But then the problem says there's somebody down here at some place you want to drop a package so that it lands there. So the question is, if you drop it out with 0 downward velocity, how far ahead do you have to drop it so that it lands right where they are? All right. And this is a fairly straightforward problem, but you can be asked a wrinkle on this problem. They can ask you, well, he doesn't drop it at at 0 velocity. Instead, he throws it down with some initial x velocity, y velocity. Or they can say, well, he throws it up a little bit, gives it a little bit of y velocity. So you have to calculate a different path. That can throw you for a loop on a test, but it won't if you've practiced how to do it and you know how to do these things. Just for your reference, you can look at this at your leisure. I've walked through how this particular problem is solved. It might help you a little bit to get the feeling for how it worked. The other kind of problem, and this is an example of how you can get a wrinkle. Somebody says, well, everybody knows about football, so we're going to say somebody kicks a punt, and when they kick in the punt, their foot is 1 meter high, and they kick a punt and it goes path, and want to know, where does it hit the ground? All right, and so the question is not how far does it travel up here to there, but how far does it travel from here to down here? And you can work it two ways. One is you can start off with that initial position and initial velocity, and then just do the full trajectory going down to some y equals -1 meter. Or you can do this with the range equation and then do this little part starting with the velocity here. But either way, you can work this problem. And it's sometimes helpful to be able to work it two ways so you can check your answer to make sure you're right. Another kind of problem, I give my students this kind of problem all the time. This is, everybody knows about Mission Impossible. So it's Mission Impossible stunt, where there's a secret agent, a superhero running from some thugs on a motorcycle. And he's got to drive up a ramp and leave the ramp at such a velocity that he goes over a fence and lands in safety. And there's a story backdrop on the thing. 30 degrees, so high, the fence is so high, although the intelligence is unclear whether the fence is 10 meters or 15 meters. And so the kind of thing that people ask for this is, find the minimum speed that he has to be going to still clear the top of the fence on his trajectory after he's. So what are they asking for? They're asking for a speed to get a max height. Then to throw it in, how far on the other side of the fence would he land? Well, that's just gravy after you've figured out how to solve the problem. Then to get the students to be prepared for anything, if he's worried the intelligence might be wrong and the fence is actually 15 meters high, how fast, how to do the problem. So this is an example of the kind of problem that you can be faced with that can throw you for a loop just because there's so much stuff involved. But the projectile aspects of it are always the same. The equations are always the same. And if you're clear in how to do these things and had some practice, which we can do, you'll get these.